now that we've talked a little bit about how X-rays are formed for diffraction, let's move on to the actual diffraction geometry. So the configuration of the machine and so forth. So the first thing I want to mention is that we talked about the generation of monochromatic, so single wavelength X-rays. And these X-rays, their wavelengths are on the order of 1 angstrom, and this is a unit you might not often see unless you're dealing with diffraction. And so 1 angstrom is the same as 0.1 nanometers. It just so happens that since X-rays are on the order of 1 angstrom, they diffract similar sized objects, right? So things on the order of 1 angstrom are diffracted. So this should ring a bell when I did the laser and the sieve demo earlier on. The reason that diffraction occurred with the light was because the openings in the mesh were on the order of the diffracting wavelength, which is light. And so that's why diffraction occurred. Here, X-rays are much, much smaller, and so they diffract much, much smaller objects. And so this works out for us because we get the interplanar spacings are on that order. Of angstroms. So this is why we use X-rays and not light or some other form, because X-rays are the perfect size for sort of probing the crystal structure of materials. Okay, so just like in visible light, XRD or X-ray diffraction is on the same principle, right? It's looking at the interference of X-rays after they react, or interact, I should say, a crystalline material. Right? So this is why we needed to kind of talk about the things that we did. I mentioned the crystal structure, right? So we have to know how to describe that crystal structure. We talked about interplanar spacings and how the reciprocal lattice discusses this. And so this is why we kind of had to have that review of all of those topics. All right, so we're looking at this interference of X-rays. And so this is just like what we talked about in phase contrast. Microscopy. So there we were talking about the interference of visible light. Here we're talking about X-rays, but the same principle applies. So we have phase differences. So when the phase difference is some integer of the wavelength, this gives us completely constructive. So that should be, that constructive should be familiar at this point. And if not, go back and watch those videos about phase contrast. And then if we have differences in phase differences that are n lambda plus 1/2 of the wavelength, this gives us completely destructive interference. Right? So those are our two kind of extreme cases in this. And we use this in the geometry of X-ray diffraction. So what I'm going to do next is I'm going to show you the sort of the simple geometry and how we come up with a well-known law that allows us to relate the X-ray wavelength and some of the properties of the crystalline material. All right, so I'm going to draw you the geometry of a simple X-ray diffraction experiment, and in doing so, it's going to discuss what you might know of as Bragg's law. All right, so let's say I have a crystalline material, and I'm going to represent it in 2D. So these are, think of these as a row of atoms, A. So this is basically the surface. And then the next row down, so we're just looking at a two-dimensional representation of this. This is B. And then so on and so forth. So I'm going to draw one more just to illustrate structure. But you can imagine there's many more layers to this material. All right. So we're going to look at this. This is our two-dimensional crystalline material, the rows of atoms, and we're going to look at a beam of X-rays coming in to this material at some angle, right? So I'm going to draw this. All right. So my beam is coming from over here. This is my incident beam. So I have one ray, and then I have the next ray, and I'll try to draw this carefully. This is beam 1, beam 2. And so when we're talking about the incident beam, our incident beam is always going to be in phase, right? So the peaks and valleys match up. In phase. All right. So this angle with respect to the material is known as theta. So this is some arbitrary angle with respect from the incident beam to this plane. So a couple other things to kind of draw here. So this is our first plane of atoms, and then you can think of this as the second, and so forth, right? Excuse me. So the distance between these is going to be the interplanar spacing for that HKL plane, right? Just that's by definition. All right, so we want to look at this geometry, and this is a very simple sort of geometry question at this point. So our first beam, it comes in at an angle, and let's say that it diffracts, which means that it's basically going exactly mirrored in the opposite direction. So this is the diffracted beam. So if it's diffracted, it's also going to be at the same angle, theta. So that, let's say that first beam is as such. So the peaks and valleys, right? It's some denomination of the wavelength. So it really hasn't changed that much. So now let's look at the second beam. So the second beam, up to this point, travels the same distance. Or sorry, up to excuse me, up to this point, right? So it has to be 90. So here to here is the same distance as here to here, and so I'm going to call that S. So that's the same distance, but you can see that there's an extra distance to this point, and basically where this atom is, I'm going to call that Q. So if this one diffracts, it's going to go again in the same direction. So it's going to be theta again. And it's going to travel the same distance up to S, but then it's going to go an extra distance S to Q, and then back over here to T. I'll call that point T. And then from there to there, they're the same distances. So basically, we have an added length SQT that beam 2 goes. So that's going to be important. So what we want to look at is, are these two beams in phase, right? Like they were before. So in phase, again, is some integer value of the wavelength in lambda. So to get that same combination that we saw, right, for beam 2 prime, they would have to be some integer value of this. So to sort of write that out, we're saying that SQ, the vector SQ plus the vector QT, so basically these two lengths, would have to be equal to n lambda for constructive interference. Right? So that's just a condition. So the extra distance has to be equal to some version of the wavelength if they're going to still be in phase. So we can write these distances, SQ and QT, with the relationship to this angle and also the d-spacing here. Because essentially we want to, SQ and QT don't really mean anything. We want it to be in relationship to the material. And so it turns out SQ and QT, if you kind of look at this and do work out some triangles and so forth, this gives us d, so the interplanar spacing, times sine theta. That's the distance. So both of these are d sine theta. So that has to be equal to, n lambda. So this equation right here, this is known, and I'll write it over here in big. If we just rewrite this, you'll probably see the familiarity of this, is that this is what we call Bragg's law. We have basically a relationship between our material and its interplanar spacing related to the wavelength of light in order for the diffracted beam to be in phase or constructively interfere. So that's where Bragg's law comes from, and it's a very simple geometric argument that we make in this case. So n refers to, so if we're talking about n equal 1, this refers to first order diffraction. And so this is typically what we're talking about, is first order diffraction. There can be sort of other orders, but really we're looking at n equal 1. So oftentimes you will just see it lambda equal 2d sine theta instead of n lambda. So that's just, again, a note that we typically look at first order, but sometimes you'll see others, but usually not in what we're looking at. All right, so here I've rewritten Bragg's law. So again, this is the physical relationship that allows us to determine the interplanar spacing d in real crystals, right? So we can construct an experiment with wavelength of X-ray that we know and determine, based on the angles that we observe in the experiment, what the interplanar spacings are. So that's the power of this. So that knowledge of interplanar spacings allows us to get information about crystal structures, and also with that lattice parameters from these relatively simple experiments using Bragg's law. So that's kind of the power that we've had. So in this, we talked about how this has to be satisfied for constructive interference. So when this occurs, when constructive interference occurs, these are known, at those angles, those are known as Bragg angles. So this doesn't, every angle that we use in the experiment doesn't result in constructive interference. Only at specific angles known as Bragg angles does that occur. At other cases, we have more destructive interferences, and so those waves are out of phase, and so we're left with a lower intensity. And so we'll see examples of that when we get to the spectra. So this equation here gives us, as you see, the interplanar spacings. But I've already shown you previously that we can take those DHKL values, for example, for the cubic system. If we know the DHKL and we know the values of HK and L, we can use that through this equation that I've shown you before here, right? If we know the values of HK and L and we know the interplanar spacing, we can get A, which is the lattice parameter, right? And for other systems, we could also get A, B, C, right? Those are all of our other lattice parameters, and we could also get angles between them as well. But this is just for the cubic system. So that's what we do when we're trying to determine what a structure is we use this Bragg geometry to calculate interplanar spacings, which then give us the lattice parameter. So for indexing, is basically, let me write it out here. So indexing, so this is where we identify an unknown XRD pattern. So we run this Bragg experiment and we get an unknown pattern, and indexing is the process by which we go through that data and determine the crystal structure and the lattice parameters. So for this process, a really useful form of these expressions. So we have Bragg's law, but then we also have this. So we can basically kind of put these two things together. So you'll often see, and we'll get to this when we get to indexing, you'll see that we're going to use this form of the expression. And it doesn't look like much now, but we'll kind of go through and see why this is useful. But basically, here, this equation, we've combined the relationship between lattice parameter and the interplanar spacing in Bragg's law. And we've written it in the form of sine squared theta because this allows us to index that structure from an unknown. And so we call this part, we call this the sum of squares. And this is sometimes written as just S. So you'll see a table that I'll give you later will have these values of S for given structures. All right, so with that in mind, let's kind of make this into an easy math problem. So think about possible HKL values for your planes, and then think about this sum of squares values. What possible values of S can we have? So in the quiz, see if you can come up with possible values of S, of what possible values of S we can have. And obviously there's an unlimited number, so at some point you can stop, but see if you can come up with a few of them to start. And then come back and we'll wrap this up. All right, so we're looking at possible values for the sum of squares term S. So we know that H, K, and L are all integers, right? This is how we write out our Miller indices. So for possible values, the lowest would be all zeros here, and that doesn't really make sense. So we won't start with that. But the lowest value we could have is if we just make one of these 1 and the rest 0. So plugging that into this expression here, 1 squared plus 0 squared plus 0 squared, we'd get 1. So our lowest value of sum of squares would be 1. And then we could increase that if we made 2 of them 1, and that would give 1 squared plus 1 squared, so that would be 2, right? And we could keep going like that. 1, 2, 3, 4, 5, 6. But if you do the calculation, you should never be able to get 7, right? That just doesn't work in here with the squares. So you actually skip over 7 and then get to 8, 9, 10, and then just keep going, right? So you don't need to know them all, but this just kind of gives you an idea of the possible values of sum of squares. And when we get to indexing, trying to identify unknowns, we'll come back to this, and you'll kind of have to remember what we did here for phase identification.